Hi, my name's Andy. Welcome back if you're returning. We are going to implement a thing that works a bit like string, the class in the Rust standard library. We're going off-piste for me. I don't know how to do stuff like this, so we'll see how it goes. And we probably won't do anything very comprehensive. We'll just get the real fundamentals up and running if I can manage it. All right, so what's this thing going to look like? Well, I think we're going to have a thing like the type of string. I thought what we'd do is we'd implement an ASCII string because it's a bit like a string, because strings have to check that things are UTF-8 and we're going to check whether things are ASCII. And it's understandable and it's conceivably useful. Now, actually, there are implementations of ASCII strings out there that are going to be a lot more useful than what we implement. But hopefully it will cover some of the ideas that we covered in one of the previous videos about the heap and the stack and stuff like that. Like, how does it actually work to like manage your own bit of memory? Because we're going to do that. We're going to do it quite manually. I was thinking we're going to be able to use box for this, and I'm thinking that we're probably not. So we're really going to be going it alone. We'll see. Anyway, okay, so it's going to look something like we're going to have a thing called an ASCII string. And because it might not, because the thing you give it might not be ASCII, we're going to have a try from instead of just a from. And then for now, we'll just unwrap it. So you're going to be able to create it from a str. And then I reckon we're going to be able to then print it out like this. All right, so let's make ourselves. So we're going to need some tests. So, like this. And let's write a test that just checks something like that. So we'll have can create from str, let's say. So let s be an ASCII string. And we'll use try from again. Maybe we'll want other ways of creating them because this is going to be inconvenient, but something like this. So you can create it, and I guess we're going to need some kind of assertion, like I guess we need to turn it into some bytes. So let's say maybe there's an as bytes method which is going to return bytes, which we can then compare with this B here will make us an array of bytes of just the UTF-8 that we provide. All right, so none of this compiles yet because we haven't got an ASCII string, so we better make one like so. Now we have a struct, but it doesn't do the things it needs to do. I know we're going to need to make it debug. We might actually need to implement debug ourselves, but for now, let's just derive it. And it's complaining that you can't do try from, right? And here it's complaining we don't know about it, so that's fine. We'll bring that in. I like to use super star actually for my tests. Okay, and now it's complaining that there's no as bytes and there's no try from. Right, so we've got a load to implement before we can have our first test passing. So first we're going to implement try from an ampersand str into an ASCII string, like so. And I guess we're going to need an error type. Now the type of error, I think the only type of error we're actually going to surface from this is if the string is not ASCII. So I'm going to have just an error called not ASCII. Where should we do this? Let's put a thing called not ASCII here. And maybe not ASCII would have some stuff in it, like maybe it will tell you which string. Like it would report back, oh, and this character of the string is not ASCII or something. So it might have a reference to the string. It might have the location, but for now we won't do any of that. Probably in this video we won't do any of that. So it's just the possible thing that could go wrong when you try and make a ASCII string from a str is that it's not ASCII. Any other errors that we come across, we'll ignore for now. So we're going to create one. So far there's nothing. It's a result because it's a try from. So far there's nothing We're not actually doing anything. There's no, like, ASCII strings don't have anything in them yet. So try from doesn't have to do much. Now we're calling unwrap here. Oh, but not ASCII doesn't implement debug. Okay. So let's just have it implement debug. Now that means that probably we didn't need to derive debug on ASCII string. I got confused because when I was setting this all up, it complained about unwrap, and I thought it was complaining about ASCII string, but it was complaining about not ASCII. All right, so there's some things that can't happen yet. ASCII string doesn't implement display, and it doesn't implement as bytes. So let's do that. So import display for ASCII string. We need to. Oh, it's the wrong display. It's the wrong display. We need to bring instead format display. There we go. That's why it was confused. Okay, now. So for now, there's not a lot we can do because it doesn't actually contain anything. So let's just write ASCII string like so, and then we'll do something better soon. And that should probably be like a question mark or something, right? Yeah. Okay, so display, the way display works, if you haven't seen it before, is it takes a formatter and then you can send stuff to the formatter. Like here, we're just sending a hard-coded string. And then once you implement display, that means the toString method is automatically implemented for you, because toString is implemented for anything that implements display. The display is like more efficient because this formatter thing is much more efficient than converting every little bit inside every little thing to a string and then sticking them all together later. All right, so one more thing. We have no asBytes method. I don't think we're going to implement a trait for that. Is there an asBytes trait? Doesn't seem like it. All right, so we're going to just import ASCII string and provide a function which takes a reference to self and returns. Well, it's going to return, I think, a slice of U8. And I think we'll just hard code one for now. Now, it's complaining that asBytes is not used because it's only used in test. How are we going to make these warnings go away? If I make it pub, does it go away? No. I guess we've got to use all these methods in our main method, otherwise it's going to complain. Let's just use it there, print out the bytes as well. Let's print out the bytes as a debug string. Let's split that in two. It's too annoying, right? So we'll print out hello, and we'll print out the bytes of hello. Another line just to make it easier to understand. All right, when we run our code, it prints out the toString of ASCII string because we implemented display, and then the bytes that you get back from calling asBytes. This is obviously wrong. If we run a cargo test, we'll see that it was expecting to get this, which is actually this new string, but has numbers because the B here means this is an array of bytes. But it got back an empty list of bytes. So now we've got to do some actual implementing if we want this test to pass. And let's try and implement it properly first time, and then we'll do things piece by piece, but this stuff I think we just need to go ahead and implement it. So the way our string is going to work is it's going to hold on to a pointer. Let's call it putter because that's what they call it in some things I was looking at earlier when I was desperately trying to figure out how to do this. So we're going to hold on to a pointer to a U8. Which looks like this. So star mute means it's a pointer where I might change the stuff on the other end of it. And the type of thing it's pointing at is a U8. And we're going to have a capacity, which is how many U8s are actually held there. And then later we're going to have a length. So let's also hold that. I think those should both be usize, but we'll see whether I'm wrong about that. All right, so in order to construct ourself, we're going to need a pointer, a capacity, and a length. And our length is going to be the same as our capacity, because the capacity is just going to be the length of the string that we were given. Capacity. So we won't check for ASCII-ness yet. Value.len. So let's rename this because it's now used. So basically, we're given, when we're doing this try from, we've been given a str. The str has a len, which is the number of bytes in that str. So that's the right thing for us. And we need to allocate some memory on the heap. Remember how long it was, that's what the capacity is, and also remember how many of those bytes are actually used, which in this case is the same as the capacity. So we need to do the allocate bit. So we're going to make a pointer, and the way you do that is you call this alloc function. I've just looked this up, so I'm just as much in the dark as you, and it's going to take a layout. Let's just see whether we can get the alloc function in. So we have to use std alloc. That's the function to allocate some memory. It's unsafe, and we need to make a layout for it. I think we call layout array, but let's bring in layout and let the compiler help us. So std alloc layout, which basically is like basically what kind of shape of memory do you want? And what the shape of memory that we want is a certain number of U8s. So we call this array function, which creates a layout describing a record for an array of t of length n. So the t here is U8s. We want U8s, and we want a certain number of them, which is our capacity. And calling alloc is unsafe. And I don't know how to talk about the safety here. Oh, and we need to, that layout returns a result, so we need to say failed to allocate. No, well, it's not failed to allocate, it's failed to... When will this fail? This will fail if the total size would exceed the maximum size. So this is, I guess, well, it's like too large. Creating too large allocation. So this shouldn't happen. And like we're passing in a str, so surely it's got to be a reasonable size, hopefully. Otherwise we'll crash. Now I need to get my code formatting right, otherwise I go absolutely mad. I think I've got a Rust format.toml that I can copy in here. Let's have a quick look at what's in my Rust format.toml. Yeah, exactly what I want. Fine. So now when I save, it lays me out nicely. Okay, good. We're back. All right. So, so we've created a pointer by asking for an array of U8s of size capacity. We've remembered our capacity and our length. So we've allocated a load of bytes. We haven't actually copied from value into the pointer. So this is like deeply unsafe. So I guess the reason this is unsafe is because we're allocating memory but not actually zeroing it. Let's see. And we've got to promise to deallocate it as well. I guess is the other thing. It doesn't actually say safety. C global alloc : alloc. Well, will you take me there? No. Right. Okay, so let's have a look if we can find that. Global alloc : alloc. Right, here we go. Safety. Layout must have non-zero size. Otherwise we get undefined behavior. So I guess we should check that. The allocated block of memory may or may not be initialized. Yeah, so, alright, yeah, so if you do ask for a 0 size, you might get back a null pointer or something else might happen. So let's check for that. Why has this gone white? Didn't I ask for... Yeah, okay, so, there we go. Okay, so it may or may not be initialized. Now we could fix that because I believe there's a like alloc and alloc zeroed, yeah, which will maybe is not unsafe, but we are going to fill the memory up, so it's fine. We'll do that in a second. So first of all, can we check for layout size? All right, so let's just check it. If layout.size is 0, then panic. Well, that might fail for... What about a 0? What happens with a 0 length string? Yeah. String too short. Let's just allow this to crash. Or let's just say allocation. If we may need to handle this case. We'll see whether we get a crash when we start testing for that case. So now our safety comment is safety. Layout size is not 0, and we will initialize all this memory immediately. Okay, so how we're going to initialize it is we're going to do some kind of, I don't know, we're going to do a mem copy. Is that a thing? Let's see whether we've got any documentation that will help us. Mem copy. Seems like there's a thing called mem copy. Stood putter copy non-overlapping. I think that's probably what we want. Again, you lose my setting. So source, destination, and count. And these regions of memory will not overlap. So I think we're happy to do that. So let's do copy non-overlapping. Which is instead putter. Alright, so copy non-overlapping. The source is going to be value, which I think we'll maybe just call it as putter on. And the destination is putter, and the count is capacity. Right? Maybe this is fine. This is also unsafe. And now, why is it unsafe? Because they must be valid for that length and valid to write. They must be properly aligned. And they must not overlap. And if t is not copy, then that would be terrible. But these are just bytes, so it's going to be definitely going to be copy. Safety. What is it? Putter is brand new and does not overlap. Value, putter. That's not how you spell putter. And also they're both value and putter have a length of capacity, so are valid to read / write for that length, something like that. Basically, we're just saying that I haven't done the thing you told me not to do. All right, so I think I think we've now got an implementation. We look for the length of the thing. We allocate. We create a layout which asks how much says how much we're going to ask to allocate. We allocate it. Then we copy from value into pointer. Now we've got the thing, and as bytes doesn't yet give us back the bytes. So let's implement that, which will just be can we do like slice : from raw parts self.putter self.len maybe? It's also unsafe. Now, why is it unsafe? Let's have a look at that. Behavior is undefined if any of the following conditions are violated. Data must be non-null, valid for reads of the right length, which we are guaranteeing, must be properly aligned, must be contained with a single allocation, yep. Data must be non-null, aligned, even for zero length slices. Don't know what that means, but we're not doing zero length yet, I think. And it must point to len consecutive properly initialized values of type T. And you must not mutate it in the interim. Okay, so when we call as bytes, we give back a slice which has a lifetime same as us, so I think we can't mutate. We'll check that, but I think we can't mutate one of these at the same time as someone holds a mutable reference to us. I mean, at the same time as someone holds a reference to this, what was returned from as bytes, I think. So safety. Putter is aligned and valid for capacity bytes, which is always, I'm saying, greater than len bytes, greater than or equal to. We return a reference with the same lifetime as self, so no one can mutate self while we hold it. I think that's right. So basically, the what asbytes actually means is that there's this lifetime which has been provided for us, which says that the return type has a lifetime the same as the lifetime of the reference to self that came in. That's all just implicit in a method like this that returns a reference. It just tends to just pick up the lifetime of the reference to self. So I think that that's true, that when we return that reference, no one can mutate it at the same time. No one's using capacity so far. It should be stood putter. Okay, it imported the wrong thing for me when I asked for copy non-overlapping. Okay, capacity is not used yet. Let's just ignore that warning. Okay, now our tests run and pass. Interesting. And when we run our program, we can see this. So, all right, our display thing is not very good, is it? Shall we make that better? So, I guess displaying an ASCII string should just write that string. So let's make a test for that. Can convert to string. So let's just call this something like this. And we're going to turn it into a string. And we get toString, as I said, because we implemented display. So toString of that should equal foobar, like so. So now we run that test. It's going to fail because it always just prints out ASCII string when you ask it to turn it into a string. So this is not right. Instead, it should be, what have we got here? Right bytes, maybe. It seem to be offering that. What can we do with this? We can write a char, write a str. We could convert it to a str by turning it into bytes. No, so this would be write str self dot as bytes dot into str, maybe, or is there a str from UTF-8? We can actually use from UTF-8 unchecked, right? Because we know if it's ASCII, it's UTF-8. Yeah, so let's try from UTF-8 unchecked self.as bytes. And this is unsafe. We'll write about safety in a second. I need a question mark, yeah. Alright, so let's do all this in a separate section so we can talk about safety. Safety. So from UTF-8 unchecked, presumably it must be valid to UTF-8, so we can say yeah, because all bytes in an ASCII string are ASCII, and this is not actually true right now, so they are known to be valid UTF-8 because all of ASCII bytes, the first 127 things, are that is valid UTF-8. They're just all the really simple characters in UTF-8, and they have the same value. All the ASCII characters have the same value in UTF-8 and in ASCII, except maybe some of the weird control characters that we don't care about. Now, we haven't actually... This safety comment is not actually true because we haven't actually checked that it is valid ASCII, but let's pretend for a second. We'll write a test for that. All right, so that test also passes. So we can convert to a string when we do cargo run. It now says hello world. Hey, look at that. And it says, presumably, hello world in bytes. All right, so let's do some checking that it really checks for ASCII-ness. That would be nice, wouldn't it? Fails, panics. No, what does it do? Yeah, fails if not ASCII. So I think we need to say something like, oh no, it's going to be, it's not panicking. We decided not to panic. So we can do try from. Now, a string that contains non-ASCII, for example, like this, some kind of, whoops, foo, but not a normal foo. That's not ASCII. And we want to do expect error. Well, do we? I think we want to unwrap error because I want to get hold of it and then see what it is. Assert matches. Well, no, we don't have that. That's some module that we need to import, so we won't do that. We'll just do a match on it. And there's actually only one thing it could be. Why doesn't it like unwrap error? Because AsciiString doesn't implement debug. Alright, so now we've got a derive debug. Fine. Okay. So E is not ASCII. So let's just do if let not ASCII equals E, do nothing else, panic, wrong error type. Now at the moment there is only one error type, so this will always be right, but this unwrap error thing. What's your problem here? Oh, this should be, no. Irrefutable pattern. If let is useless. Okay, so we could just, the problem is, can we just assert eq here? Problem is, this is kind of a pointless thing because there is only one type that it could be. Not ASCII needs to be able to do equal, but we can do that. Alright, so now hopefully our test will pass. No, it didn't pass because we don't do this checking. Good, okay, so our test was actually pointful. The pointful bit of it was the unwrap error part that says this should be an error because this is not ASCII. So what we have to do is actually do some checking in here that this string is suitable to become an ASCII string because we've been given a str. So I guess we just loop through the characters, or we could loop through the bytes. Would it be safer to loop through the characters if sure is greater than 127? Return error, not ASCII. I think it's as simple as that. We just need to make this happy. Can we just say I'm quite surprised that it didn't just recognize 127 as a character already. Well, we can just unwrap that. This is so awful. Why is it so painful? Does that work? Does the test pass? Test passes. Okay. Are we happy with this? Can we do something else? Oh, we can do this. Fine. That'll be better. What does that do? Does that do the same thing? Oh, no. That's no, that's not the same thing. We want is ASCII, not is ASCII digit. There we go. Let's have a look at what that does. It casts to a U32 and checks that it's less than, I think that's 127, right? So I guess we would have come to approximately that if we'd been clever enough. All right, so our test no longer passes because we're panicking at line 84. Because new string it thinks is not ASCII. Oh, yeah, because I forgot the not there. Fine. All right, so now we're passing. We have the ability to make one of these strings. We have the ability to turn it into bytes. I guess we have the ability to turn it into a str, which we've implemented in the middle of that display implementation down here. It'd be quite nice to have that making it into a str be available, not just in here, but generally available. but we've already got 2 strings. So for now, we're probably not too bothered. We can do 2 string on it. We're guaranteeing that it's ASCII by checking all the characters on the way in before we do any of the scary stuff. And there's only one way to make an ASCII string at the moment. And that does guarantee. So what we haven't done is empty strings, but the really interesting part is when we resize this, so when we start adding stuff to it. So first of all, let's just check that when we've called AsBytes, we can't. I mean, this is obvious, but just to double check the reasoning that I was having earlier. We've got this AsBytes thing here, so let's just do it here. I think we won't keep this code. Let b equal s.asbytes. Let's make s mutable. And then we'll try and modify s. Oh, we can't at the moment. Okay, we're going to need some kind of way of modifying it. So it's going to look something like try from more dot unwrap. Now we don't have a plus equals, so we're going to need to implement that. Is there anything we can do to modify s? Not right now. And then we're going to we'll just print out b later, right? Okay, so this is like a test that I had in mind for checking that you can't modify it while you're holding a reference to it. But we can't do that yet because first of all we need to do just can make a string longer. So here's where it gets interesting. And we probably won't go too much further than this because I've been making really silly long videos. And can append another ASCII string. Right, so let's just make 2. Let s1 equal ASCII string. Try from str1 and s2 can be str2 and s1 plus equals s2. We better make s1 mutable. And then I guess we'll just assert that the 2 string of it comes out how we like. This is why as_str would be quite nice. But, we can figure out how to do that. We've already done it, haven't we? So it should come out as str1, str2 like that. Should be an s1 there. And we need to implement plus equals for this to work. So how do we do that? Well, we're going to do another impl add a sign for ASCII string. Like so. So you can do plus equals of different types, in which case you would put the type in here. But if you miss it out, it defaults to the same type as you, and that's useful for us here because we need to check that the other thing is ASCII before we combine them together. All right. So the point of this is that we're going to. So we haven't done drop. We need to somehow check that drop gets called. So otherwise, we're leaking memory all over the place. It's terrible. So let's just write down somewhere. We need a test for. Test drop somehow. I don't know how to test that actually. Maybe we just have to implement it and not test it. That would be awful, wouldn't it? Okay, so when there are 2 cases that we have to deal with here. One is that there's already space, in which case we don't need to allocate a new pointer. We can just copy the bytes into the right place. Or in the other cases where there isn't space, and therefore we need to do another allocation. So far we've only seen strings that have a capacity equal to their length, so there's never space. But in principle we've left this capacity there because we might have extra space, and we're about to use that, so that's going to be cool. And yeah, when we test this stuff, we'll then test this test here is going to test that straw. Oh, these are the same length as each other, so let's just make that different length. So then if we went wrong with length and capacity, maybe we'd get some kind of garbage digit at the end here or something like that, or a nil or something. So depending. So what we need to do is check whether there is space already. So what we need is like the required capacity. So the required capacity is self.len plus the length of the right hand side. Oh, now we don't actually have a len method on AsciiString, but we should. So let's add one of those. Just to basically line up with how string looks. So we could, it was offering us to just use the member, but we're going to want this to be a public function, whereas len is going to be private. That would be the idea. Now we're not doing public and private in this because we're doing it all in one file, just because we're not doing everything. Right. So the required capacity is the length of us plus the length of the other one. I guess we could call len here. Would that be better? Don't know. Notice they're both length, not capacity. Doesn't matter how many bytes there are in right hand side. It matters how many bytes we're going to copy, which is len. Okay. And then we just need an if self.capacity is greater than or equal to the required capacity, then there's no need to reallocate. No need to reallocate. Otherwise, there is a need to reallocate. So if we're going to reallocate, we need to do something like this, right? We need to create a new allocation and then copy some stuff and then deallocate the old allocation. So it's going to be, we're going to need required capacity. And we're going to allocate it. So this will be a new putter. We're not actually going to initialize all this memory. So that's interesting. We'll initialize this memory up to the new len. Oh, I'm doing this a bit wrong. But this is still true. So this should be new len. So what we generally do when we increase a capacity, we need to do something in here, by the way, but not yet. When we increase the capacity, we don't just increase it to exactly what we've been asked for. We tend to bump it up by a certain amount so that there's a bit of extra space in case we don't, so we don't allocate every single time we append stuff. So we actually need to find a new capacity which is potentially bigger than new len. So we want to do something like new capacity. Set it to be capacity, and then while new capacity is less than new len, we are going to increase new capacity. So basically, we're going to make new capacity bigger in chunks until it's big enough to fit our new thing. Now, often, I think I've read that Rust does this, that it increases the capacity by doubling it. Now, I've read somewhere that it's good to do 1.5, which of course you can't do with integers. So we're going to do this. Multiply by 3, divide by 2. That's 1.5 approximately. So, yeah. So we're increasing our capacity. Oh, I'll tell you what, this is just going to make our testing a bit harder, isn't it? Should we just double it? No, I like this. I like this because I think it has better patterns of, I don't know. It's silly, but I'm doing it. All right. So now we've got this new capacity. The allocation we're going to do is for new capacity, not just new len. And then we're going to copy bytes. First of all, we're going to copy bytes from self into putter of self.len. And then we're going to copy from, what's it called? Right hand side dot putter into putter plus self.len. And the amount we're going to copy is right hand side dot len. Now, it doesn't want us to add a usize to a star mute 8. Apparently there's a wrapping add or just add. What if we do dot add? Is that okay? Seems happy. All right, so let's talk about safety. So we checked the layout size. It wasn't 0. We'll initialize this memory up to the new len. That's what we said, isn't it? And we never allow more than new len bytes to be read. All right, so let's talk about safety for these two things. So first of all, putter's brand new and does not overlap self.putter. That's true. Both self.putter and var have a length. So both pointers, well, what is it? It's basically self.putter is valid for at least self.len, and putter is valid for self.len plus right hand side .len. So this fits. And then here we've got another safety comment we need to do. Putter is brand new and does not overlap right hand side .putter. So we're kind of reaching inside right hand side here to do this, but I think it's okay. Right hand side .putter is valid for at least right hand side .len, and putter is valid for self.len plus right hand side .len, meaning we have just enough space in it. No, putter is valid for new capacity, which is greater than or equal to that, meaning we have at least enough space. In putter for this copy. I guess that's good enough. It at least indicates we've thought about it. So we've allocated at least new len space, where new len is the two lens added up. We didn't finish this while until new capacity was bigger than new len. By the way, like at some point maybe this could take a long time or something, I don't know. So maybe there's a better way of doing this. I'm sure there is. I'm sure we don't need to loop. But anyway, it doesn't really matter for this. we've allocated that much space, that new capacity space. So now we've definitely got enough space for putter plus self.len plus len. That'll still be within putter. Hopefully. So we copied all the bytes from there, we copied all the bytes from there. All looks good. I think our test might pass. It did not, because we've done all these allocations and we haven't actually done anything with them. And we haven't done any deallocations either, so we've got a way to go yet. So, well, I don't know. We can just leak some more memory and make our test pass. So now we can just say self.putter equals putter. Self.capacity equals new capacity. Self.len equals new len. There's already a mutable pointer to self because this is the add assign function. And now our tests pass, but we haven't done any deallocation, so we're very, very bad. We've leaked all kinds of memory. Can we show that? If we just, do we have val grinds? If we just val grind this thing, yay, look, it tells us we've definitely lost 36 bytes. So that's interesting, isn't it? So so valgrind is a memory checker that checks how much, among other things, tells you how much memory you've leaked. So let us try and fix all our memory leaks and see whether we can make valgrind better. So first of all, now that we've copied out of the old self.putter, I think we can deallocate it before we then overwrite it with this new thing. So that's going to be unsafe. We'll have to look at why it's unsafe in a second and write ourselves a thing. But I guess we should call this dalloc layout. And that's going to be an array of U8s of size self.len, right? We're just deallocating the old stuff. So it should be dalloc layout. Why is our code such a mess? That's what I want to know. And that should be, let's just unwrap that. It shouldn't fail, right? Since we managed to allocate it initially. So, all right. So we've got rid of one of our leaks. So now if we run valgrind, hang on, did I not save? Yeah, we only lost 31 bytes. So we've saved ourselves 4 bytes of leakage from that fix that we've done there. So yeah, so let's just talk this through. So add assign takes in right hand side, but it doesn't it takes ownership of right hand side, but it doesn't take the bytes out of right hand side, right? The only bytes, the only pointer stuff that it's mashing is its own pointers. So it figures out how much space it needs. It allocates a new pointer with that much space, copies from both sides into it, and then it deallocates the old memory. So this dalloc says just that, like, I'm no longer using this bit of memory, and then it overwrites putter with the new memory it's just allocated. So I think that all makes sense. Let's have a look at what the safety is for dalloc. See, global alloc : dalloc. Right. Let's try and find that. Here we are. So safety, the caller must ensure pointer is a block of memory currently allocated, and layout is the same layout that was used to allocate it. Oh, you know what? I think I've got a bug. Yeah, that shouldn't be self.len. That should be self.capacity. That's bad. That's bad. That's a bad bug. And we would never have found that. All right, still only leaking 31 bytes. So, yeah, dalloc is safe because... So that's a good example, by the way, viewer, of the kind of bug that unsafe code can have where maybe the dealloc code wouldn't have deallocated all the bytes that we allocated, or it would have crashed because we tried to deallocate with a different length from what we provided it, or something, and we would have just never, the compiler would not have helped us because we're in unsafe land. All right, so we allocated initially using the capacity. So this. So this is the right size. We are just about to overwrite self.putter, so we won't use it after freeing it. So I really feel like this code is like got out of control, like how long these functions are. So I would definitely be like refactoring this, and like there seems like there's a lot of commonality here about like creating a layout and allocating and stuff. So I would probably write some helper functions for that. But we're just getting this working for now. This is just kind of prototyping. So let us, we have found a way of checking that we deallocated. I don't really think we can unit test the fact that we've deallocated. Maybe I'm wrong. Maybe you could leave a comment, tell me how we could test it. But let us fix the other bug we've got, which is that we're not deallocating when this thing gets dropped. So we'll impl drop for AsciiString. And what we need to do is deallocate putter. I think it's going to be very similar to what we just did. We are being dropped, so self.putter will not be used after it is deallocated, I think. So yeah, I'm probably doing everything wrong. So let me know in the comments what I missed or what I've done wrong. All right. How much memory are we leaking? None. Yay. All right. So we're doing really well. We've handled completely the case where we needed to increase the size. Let's do a bit of refactoring. It'll make our lives better, won't it? All right. So let's first of all get allocation into a helper function. I guess our safety guarantees are going to be a little bit harder if we do that. All right, let's not. Let's leave it as it is. What we can do, I guess, is just take this branch and put it into a separate thing so it's not quite so confusing. Let's call this function. Why is it a method? Does it need to be a method? I guess it uses self.capacity. All right, yeah, okay. So we'll call this reallocate add assign. Was it add assign that we were implementing? Yeah. So now we're going to say that we're going to do some other thing, which we'll call self.no allocate add assign. Add assign. Passing in right hand side and new len, I guess. Do we still need that? Probably. So let's make a method called no allocate add assign. Definitely doesn't go here, mate. Goes here. No, not quite there. There. That's how to confuse the compiler. It doesn't return anything. It does modify self though. So we've already decided that we've got enough space. So we don't need to do any allocations, but we do need to copy some bytes from right hand side into somewhere near self.putter. So we need to copy from right hand side .putter into putter.add self.len. We need to copy right hand side .len bytes. Should be self. So we need, yeah, I guess add is doing what we wanted. Yeah, it's returning the modified thing. That's what we want. Yeah. So we're copying out of right hand side .putter into self.putter, but len far along, and we're copying right hand side .len bytes. And I guess this is kind of unsafe. Unsage. Because we don't really need new len. Interesting. Let's not have it then. Now the reason I'm saying it's unsafe is we need to be able to trust the person that calls this, that they've checked that there is space for right hand side after len. So our safety comment on this is going to be safety why do we do that? Something like that. There must be space after self.len, so space in self.putter for self.len plus right hand side.len bytes. So I guess like another way of saying this would be when we allocated self.putter, we allocated more than self.len plus self.right hand side. So plus right hand side.len bytes. So I think that's simple enough. And then here we can just say safety. There is guaranteed the safety properties of this method guarantee that there is space in self.putter for right hand side.len additional bytes. So putter doesn't change, but self.len equals self.len, or I guess plus equals right hand side.len. Right, so we're modifying stuff inside that allocation of pointer, but not modifying pointer itself. We're not modifying capacity, but we are modifying self.len. Now I've implemented that without testing it. So let's now just get rid of that implementation completely and get ourselves a failing test. So how will this happen? So basically what we need to do is have quite a long string. We've done that. Let's just say drop is tested. Was tested by running the tests through Valgrind. Trust me. Trust me. Alright, so let us make quite a long string. Can append multiple times. So let's have quite a long string. This is quite a long string, and then we're going to append str2 onto it. Let's just make it all caps or something to make it easier to understand, like so. Add one onto the other. Well, first of all, we're going to assert that the capacity of S1, which I guess we should have a method for, is, I don't know, some quite big number, right? How long is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So 27 times 1.5 is like 40. So it's going to be about 40. Let's make a capacity method next to the len method. Again, just to match what you can do for strings. Okay, that's moaning that's not getting used because I'm only using it in tests. For goodness sake. No one cares. Then is len used? Why is it complaining about capacity and not complaining about len? I don't know. Let's use it. Capacity. Hello.capacity. Alright, while we're here, now that we can do plus equals, let's check that this doesn't work. Cannot mutate immutable variable s, right? Well, let's make it mutable. Cannot borrow s as mutable because it's borrowed as immutable. Okay, so this is what I was saying earlier. Because as bytes returns an ampersand a bracket U8, that the lifetime of that is s. So B stays alive, and therefore you can't modify s while B is alive. If we got rid of this, so B isn't actually being used, then we'll be allowed to do that. But anyway, all right. So that just checks that at compile time we're protected from giving back bytes that then change underneath you. Anyway, so the capacity should be 40. The final string should look like what we expect. Well, let's add some more now. So let's add another thing on. So let's just check the capacities right then. Now we'll add another string on it. And the capacity should still be 40. And the final string should look like this. And that feels like, let's just have a comment here. We didn't need to reallocate. Now this will fail because we just commented out the code we just wrote. Yep, it did. So now let's comment back in the code we wrote. It works. Let's run it through Valgrind. No leaks and no other problems. Valgrind would find if we did something terrible and overwrote memory. So maybe if we insert a bug here. So maybe if we swap over these two, that would probably be a nice bug to have, wouldn't it? Maybe it's going to crash or something. Oops, no, I need to recompile it. Okay, so definitely something bad happened because look at these zeros in here when it was supposed to be str3. And those zeros I reckon are copied from invalid memory that happened to be 0. When we run it through Valgrind, whoa, something bad happened. Yeah, you see? We caught it for us. So Valgrind is incredibly useful. Yeah, conditional jump or move depends on uninitialized values. So basically we're reading uninitialized memory. This is why unsafe code is hard and you shouldn't do it. Need to build it, run the tests, no errors. All right, so we did it. All right, so I think that's probably enough, but let's talk a little bit about what we actually did. What does a string type look like? Well, it has a way of creating it. So the way we create it is this try from, but then you might have just a new or a from or something like that. And it checks the validity. So this is very similar to string, which checks that it's a valid UTF-8 if you construct it from bytes. If you construct it from a str, that's already been checked as valid UTF-8, so it doesn't need to check it again. But yeah, it checks it, then it allocates some memory and remembers the length and the capacity. So the basic structure of a string is it's a pointer to a bit of memory, it's the size of that bit of memory, and it's the amount of that memory we're using right now. And then if we've already got space when we add on more characters, then we don't change the capacity, we just copy from the new thing, from the right-hand side thing, into the right place in our already allocated memory, the right number of bytes. And then we change our length. So it gets longer by the number of bytes in that right-hand side. But if there wasn't space, then we have to figure out a new capacity, and I've done it by like multiplying by 1.5 enough times so that it's long enough. You could just double it. By the way, you really don't need a loop for this, but who cares? You can definitely do something much better than that. Then we allocate some memory. So we do that by creating this layout thing and then calling alloc. Then we copy the bytes from our existing string into our new pointer, from our existing pointer into our new pointer. We copy len bytes, and then we copy into our new pointer, but further along, self.len along. We copy from the right-hand side's pointer, the length of the right-hand side. Then we deallocate. Now that we've copied everything out of self.putter, which we did here, we can now deallocate the memory that was allocated for self.putter using the same size that we did when we originally allocated it. And now we've got that new pointer that we store along with the capacity and that length, which is the length of the two of them added up. And that's basically it. Then we've got the same kind of allocation code that we've already talked about for constructing from a str. This is simpler. Obviously, it just copies from the value you were given once it's allocated the right amount of memory. And then, modifying is just checking which of those two branches we take. Either we have to allocate or we don't have to allocate, and then we take the two branches we just described. And then when we drop it, we are responsible for deallocating self.putter. If we didn't do this, we leaked memory. So if we did that and our program kept running, eventually we just run out of memory. But because we checked it with valgrind, we can say that all the code that we've written so far, the functions that get called, don't end up with any memory leaked. Of course, there may well be all kinds of mistakes in this code. Other than that, what did we do? We just allowed you to turn it into a string by implementing display. We provided a very unhelpful error message that tells you something's not ASCII. And now you can use this string kind of like a string. You can give it strus and it'll crash it'll give you back an error if it's not suitable to be used as an ASCII string. You can add them up onto each other, and we could have implemented all kinds of other adding and stuff like that. Guess the thing we haven't checked is what happens with empty strings, and I feel like it's going to fail. So let's double check that. From empty str. Now, what happens when we do that? It fails because, so we actually, if we were going to do this, we would need to special case zero length strings. So I don't think we'll do that. But maybe we could just talk about what we would do if we did do it. So basically, all these places where we're trying to allocate memory, you're not allowed to allocate zero length of memory. So I guess the normal thing that you would do then is hold a zero value in putter for any situation where you would have allocated 0 bytes. And then, so you could do that with some kind of enum, but given that we're manipulating raw pointers, what I might well do is just say if putter is 0, then that means we didn't allocate any bytes at all. And if that happens, we need to check everywhere we use putter. We need to check whether it's 0 or null first before we use it. So there'd be a bunch of ifs scattered around for places where we use putter and where we use the putter of right hand side, which obviously also might be null. But if we just handle all those cases, I think then zero length strings would work fine as well. All right. I hope you enjoyed that. I did. When I initially had to look up this stuff, like how do you allocate, I was hoping I could use a box or something like that. Maybe there is a way I could use once I've allocated, I could use a box to look after the deallocation for me. There probably is a way. But it was quite instructive to me to manually do the deallocation. but probably Box could have done it for me. And this copy non-overlapping. Once I'd looked up alloc and dalloc and layout, it kind of seemed, assuming I haven't completely messed it up, it seemed approximately what I was expecting to be able to do. But yeah, it's quite fun, I think, to just get your head around the fact that a string or a vec or something like that is just like that chunk of stuff allocated on the heap, where you keep track of how much you've used, and also like you keep track of how much you've allocated and separately how much you've used. And then that allows you to expand within the capacity that you have without reallocating. And then once you realize you do need to reallocate, you can reallocate this decent sized chunk so you don't do it too often. That's basically how a string works, I'm going to claim, and how a vec works. Although I do think they multiply by 2, which I've definitely read is a bad idea. Anyway, hope you enjoyed. See you next time.